right, so in number 14, we have a wind-driven ice boat has a mass of 400 kilograms. The boat starts from rest and reaches a speed of 16 meters after traveling a distance of 16 meters. The coefficient of kinetic friction between the ice and the runners is 0.100, so I know that there's negative work. If there's a coefficient of kinetic friction, then there's negative work because friction always opposes motion. But the question is determine the work done on the boat by the wind. That's positive work. So in writing my equation, I'm going to write KO plus UO plus the work due to the wind, which will be a positive work, that's the unknown in this problem, minus the work due to friction, which is going to be a negative work, and that's equaling KF plus UF. So the F on the right side of the equation stands for final, and the F on the left side is the friction. So first thing I want to do whenever I do these problems is see if I can make anything zero. Well, we're on a level, we're on ice. Ice freezes horizontal, so it's a level surface. So what can I make zero here? Both potential energies. UO is zero and UF is zero. We're not going uphill or downhill if we're on ice. What else is zero? KO, because the boat starts from rest. So that's what I have left. I just have these three. Now, the work due to the wind, that's our unknown. So really, the work due to the wind, which is our unknown, is going to be KF plus WF. So I just need to I need to figure out what those two numbers are, and then I'll know what the work is due to the wind. So the work due to the wind is going to be, I know the formula for kinetic energy is 1/2 mv squared. So it's going to be 1/2 mvf squared plus the formula for work is force times distance. Well, the force is friction. So it's friction times distance. And I'm going to erase that because friction, I want to write it in terms of the coefficient of friction. And just like that problem we did yesterday with the puck, we can replace the friction with mu mg. Okay, so that second equation there, this thing, can be written as mu mg and then times d. So mu mg is the friction, because friction is mu Fn, Fn equals W, W equals mg, so you basically get that. Mu mg is your friction times d. And now we have all of those numbers that we can use to solve this problem. So plugging in the numbers, we're going to have 1/2 the mass of the boat times the final velocity squared plus mu mg d. And I don't have to put and again, I've already taken care of the direction of this up here. So I know friction would be a negative work, so in doing the algebra, it ends up being positive down here. So all the numbers here, I don't have to worry about signs. They're all going to be positive. So the ice boat is 400 kilograms, so that's going to go there. And that's going to go in this one. The coefficient of friction is 0.100. The final velocity is 16 meters per second. Gravity is 9.8 meters per second squared. And this ice boat is going to go 60 meters across the ice. So that's the distance through which the friction would be acting on it. And solving that, whatever that is, that's going to be your answer. So that came out to be for 14, 74,720 joules. So this is your typical problem. When you're dealing with friction, you're probably going to see like mu mg. Like if it's friction, usually we're on a level surface, so the normal force and the weight are equal, so pretty much you can replace friction with mu mg in these problems. You don't have to have a picture. I'm not requiring it. I did put a picture when I did the puck problem yesterday, just to show you where it comes from. But you can, we're doing energy, so I'm not giving you or taking off points for the picture. Yes.
Do we have to ever write down a map or not?
In this, you don't have to. You can go right to this because I know when I look at this, I can see that's the mass, that's the velocity, that's the mu, that's the m, that's the g, that's the d. So I can see it. You are writing down the facts. You're just putting it from the equation. You're going right to that. So you don't have to do that. Okay. I always begin with the beginning of the year with straight line motion. You know, I want that fourth step that you list your facts, you pick the right equation. You get used to doing that. But then when you get to these problems like this, at this point, you know, once you have the formula, the starting point of energy problems, I believe, I like it to start with the conservation of energy and then work from that point. All right, any other questions?